Hello, my name is Nicolas Foglia, and today we are very excited to present you the new features implemented in ORCA 6 regarding optical spectroscopy calculations.
Hello everybody, I'm Dimitrios Manganas. Also from my side, welcome to ORCA 6 release event for the next 20-25 minutes together with Nicolas, who will explore together ORCA's new unified theoretical optical spectrometer. Nicolas, the stage is yours.
The light absorption is one of the most fundamental experiments in optical spectroscopy. The intensity of the measurements may be estimated by a theoretical approach starting from the transition rate expression obtained via Fermi-Golden rule. This formulation allows us to describe oscillatory strengths which are proportional to the area under the absorption spectrum as the square modulus of the light perturbation. To obtain an expression for oscillatory strengths, it is necessary to model the light-matter interaction. Following a classical electrodynamic approach, the scalar and vector potential, which describe the light, may be introduced into the Hamiltonian, producing an expression for the transition moment known as the full semi-classical field-matter interaction. By taking different orders in the expansion of the exponential term of this full semi-classical interaction, it's possible to obtain different multipolar approaches. For example, the zero-order term produces the well-known electric dipolar approximation, while the first order shields the electric quadrupole and magnetic dipole interaction. In addition, two possible sets of equations may be derived for each order of the light-matter description. The first one is expressed in terms of the linear momentum and is known as the velocity formulation, while the second one, expressed in terms of the position operator, is known as the length formulation. In this circular dichroism case, the intensity is obtained by taking the difference between two absorption spectrums, one using left circularly polarized light and the other one using right circularly polarized light. Thus, all previously mentioned expression in the absorption case applies also for circular dichroism. Simply, the equation need to be adjusted, including the correct polarization vector of the light to represent left or right circularly polarized light. In ORCA 5, the implementation of absorption and circular dichroism spectrum were module-specific, leading to inconsistent calculation options, keyword controls, and output format among different ORCA modules. Additionally, as Frank mentioned yesterday in his presentation, the necessary integrals were computed multiple times during the calculation. In ORCA 6, we completely rebuild the spectroscopy computation process. Since all transition moments required are obtained by using one body operator, the matrix elements can be derived by taking the trace of the requested operator multiplied by the transition density. This key point allows us to unify the spectroscopy implementation across all Hermitian electronic structural methods. Integrals and transition densities are computed first, and then they are combined to generate the spectrum by using the new ORCA tool called One Photon Spectroscopy Tool, or OPS. This generates the availability of all Gaussian implementation in all ORCA modules in a completely consistent way, which includes printing styles, keyword control. Additionally, OPS connects directly the transition moment to ORCA ESD for those cases in which the nuclear effects need to be taken into account. For example, to request the calculation of the absorption spectrum under an electric dipolar approximation, now you just have to include the keyword do dipole length if you request to use the length formulation, or do dipole velocity if you request to use the velocity formulation. And this applies to all ORCA modules. Here is a simple example, the calculation of parabenzoquinone under a GDDFT using symmetry. In this case, the first four spin-allow excited states has been ascribed to the B3G, AU, B2G, and B3U irreducible representations. Now, ORCA 6 presents these assigned labels of the initial and final state in the first columns of the absorption table, followed by the transition energies, wavelength, and oscillator strengths. If you need to go beyond the electric dipole approximation, the keyword do higher moments requests the inclusion of the first-order light-matter interaction, which includes electric quadrupole and magnetic dipole. When this keyword is used, additional tables are printed, including desk contributions for the oscillator strength. And same as the electric dipole case, length and velocity formulation may be requested using the same keywords as before. Finally, it's also possible to request the use of the full semi-classical field-matter interaction to compute oscillator strength. And this is done by including the full semi-classical keyword, and the result is printed in the corresponding table. For specialists, particularly in the X-ray community, the keywords decomposed force length and decomposed force velocity request additional calculation of intensity using origin-adjusted and origin-independent multipolar formulations. For these cases, please consult the manual for more information and reference. And the results are printed in the corresponding origin-adjusted and origin-independent table. As mentioned earlier, circular dichroism are closely related to the absorption and may be requested just by including the do-CD keyword. In this case, the do-dipole length and do-dipole velocity keywords control the representation of the electric dipole moments in both length and velocity formulation. And in ORCA 6, we included a new feature to use the full semi-classical interaction to compute circular dichroism. The results in those cases are presented in a similar tables as the absorption case. Here I show you the results for the camphor molecule using the length formulation, using the velocity formulation, and using the full semi-classical light matter formulation. All these features are available in all ORCA modules and also in transient spectrum calculation in TDDFT and MRCI. We also included a new transient spectrum calculation in CASSCF as requested in the forum, and the keywords to use are exactly the same as the TDDFT case. The one-photon spectroscopy tool also includes a special implementation for non-Hermitian theories in which the left and right solution are not the same, such as the case of ORCA MTCI. So this includes equation of motion kappa cluster and similarity transform equation of motion kappa cluster, and also the new implementation for unrestricted case has been introduced by Marcos Casanova today. The one-photon spectroscopy tool has also been implemented to compute absorption and circular dichroism spectrum, including spin-orbit coupling and spin-spin coupling corrections using quasi-degenerated perturbation theory. All gauges are available using the same keywords I mentioned before. In these cases, because the multiplicity of the relativistically corrected states is not well defined, the average multiplicity is printed, while the rest of the tables maintain the same.
Moving forward, in the exact same way, one may perform absorption or X-ray absorption spectroscopy in ORCA. One can also perform X-ray emission following the cross-section expression for the spontaneous emission. Hence again, at any theory level, for example, methods that are based on orbital energy differences or wave function-based methods like CASSCF or MRCI or ROCIS and so on, one can actually use them to compute X-ray emission spectra, for example, K-alpha or K-beta, mainline or valence to core X-ray emission spectra, at any transition moment approximation, as exactly was described for the absorption type spectroscopies. Let us now use an actual example of a unified X-ray emission spectrometer. Focusing on the restricted active space X-ray emission spectroscopy RIXS methodology, which is a well-established approach that may be used to compute K-beta mainline X-ray emission spectra, conventionally, one would start from the MRCI module and would simply formulate the respective RXES excitation space within the RAS approach, that is to rotate, for example, 1s and 3p orbitals into the active space and get one particle excitations from this space into the D cell where a full CI excitation space is defined. One can now perform the exact same calculation within the CASI-CF module as we do in MRCI, and we do so also for other modules like LFT modules. Because the only thing that needs to be defined is the RAS space that is now defined in the MRCI, CAS, and so on module the exact same way. To activate the generation of the spectra, one needs only one keyword that is called RXES SOC, because periodic coupling is important for the generation of the spectrum. And of course, one needs to also specify and indicate the core ionized orbital. Again, the spectra can be computed into all available transition moment approximations. And for the case of iron hexachloride, for example, these spectra are shown within the electric dipole approximation here in red and the full field matter interaction operator in blue. Resonant X-ray emission, in general, resonant inelastic X-ray scattering RIXS spectroscopies can be accessed by the Kramers-Heinsberg-Dirac formula, which provide access to the direct and total polarizability tensor cross-section expressions in the case of resonant or near-resonant conditions. Again, transformation from many particle states to one particle state expressions is straightforward, providing access to RIXS type of calculations to actually any level of theory. As in non-resonant X-ray emission spectroscopy, the calculation request to X-ray absorption and resonant X-ray emission or RIXS spectra is very similar. For example, in the case of 2p3d RIXS for the iron chloride, iron tetrachloride, within the CASI approach in CASI-CF module, one constructs a basic input for the X-ray absorption spectrum, while for the generation of the RIXS spectra, one actually needs to activate only one keyword, in this case, the RIXS SOC keyword, because periodic coupling is important for this type of spectroscopies. Then again, one can compute this iron LH X-ray absorption spectra in different approximations, like the electric dipole approximation or full field matter interaction operator, and compare actually to experiments here shown in black. Then, as it will be also described in more detail below in the presentation, one can specify the desired 2p3d RIXS spectra to be generated along predefined incident energy positions that would give valence energy transfer spectra that are actually equivalent to UV spectra. It is well known that 2p3d RIXS spectroscopy opens the intensity channels of spin-allowed and spin-forbidden transitions that could not otherwise observed in conventional UV spectroscopy. Going further, incorporation of nuclear motions in electronic excitations is activated via the excited state dynamics ESD module in ORCA, which is a well-established methodology towards band-safe computations of optical absorption and photoluminescence spectra in the framework of Frank-Compton and Herzberg-Teller coupling schemes. In ORCA 6, the arsenal of the ESD methodologies has been expanded to include circularly polarized spectroscopies like the natural electric circular polarized Dichroism, ECD, as well as circular polarized photoluminescence and magnetic circular polarized dichroism. For the latter, we're not going to expand further in this presentation. As it has been shown, this can be trivially done by modifying the master correlation function to incorporate, in addition to electric dipole, magnetic dipole contributions. Hence, with all these methodologies at hand, one can very easily probe absorption or ECD, photoluminescent or circular polarized photoluminescent spectra on classes of compounds from actually organic and transition metal chiral molecules to also solid materials. To aid the computed spectra visualization and analysis, ORCA bears utility programs. One of those, ORCA Map SPC, is a utility program that can process and convolute any kind of ORCA computed spectra. In ORCA 6, ORCA Map SPC has been unified and simplified so that it's able to process all kinds of spectra in all approximations as they are computed within an ORCA calculation. For example, ORCA Map SPC can process spectra that are computed in all available approximations within one calculation, for example, spin-orbit coupling corrected absorption spectra in length, velocity, or full field matter interaction operator approximations, or actually it can process multiple spectra within one approximation. That means, for example, when we compute a spectrum using combined electric dipole, magnetic dipole, and electric quadrupole contributions that are computed in length, velocity, or origin-independent velocity approximation, all the spectra can be actually processed automatically by the ORCA map-SPC utility. ORCA map-SPC can also be used to process resonant X-ray emission spectra or RIXS spectra to generate various types of basically RIXS planes and the respective X-ray absorption and the resonant X-ray emission spectra that are generated at constant incident energy or emission energies. Another very practical tool is the ORCA plot utility program. Most of you would be familiar in using ORCA plot in your everyday scientific life to generate, for example, orbitals or to do some basic analysis with the densities in the TD-DFT calculations. In ORCA 6, ORCA plot is fully integrated to process all available densities that reside in the density container. There is a new menu section for this called Perform Density Algebraic Operations, in which, for example, one can do simple algebraic operations, additions, subtractions, multiplications over pair of densities. For example, having available the SEF Hartree-Fock and CCSD electron densities of a simple molecule like pyridine, one can actually generate the difference density and bring it in a form that can be directly visualized, which actually look like this. And moreover, these new densities is saved back into the density container and can be further used for further algebraic operations. An equally important functionality is that having available excited state transition state densities, one can use them to post-generate all kinds of natural transition orbital NTOs or natural difference orbitals NDOs of any desired excited state that is obtained within practice any excited state method of choice from TD-DFT to RXES to custom RCI. For the case of pyridine, for example, one can use the keep transdensity functionality and store all the generated transition state densities within a TD-DFT calculation. And then by choosing the transition density to the first excited state, one can generate basically the donor and acceptor NTO orbital pairs in a form that can be visualized directly. We hope in this way that the usually very convoluted excited state analysis of spectra may become a more like routine analysis for the average user. Okay, this brings us to the end. We hope that you will enjoy ORCA's new theoretical optical spectrometer. From my side, have fun with ORCA 6 and enjoy the rest of the event.
Thank you very much for your attention. We hope you enjoy using the new spectroscopy tools in ORCA 6. We are now open for any question you may have.